Welcome to AI Frontiers, where we explore cutting-edge research shaping tomorrow's artificial intelligence. Today we're examining strategic forgetting, the future of AI learning, based on 18 groundbreaking papers in computer science machine learning, published on December 11, 2025. These revolutionary findings span attention mechanisms, adaptive learning systems, physics-informed AI, and interpretable neural networks. We'll explore how machines are learning to forget strategically and why this paradoxical approach might be the key to creating more human-like, trustworthy, and intelligent artificial systems. Picture this remarkable scenario. Somewhere in a research lab right now, a machine is learning to forget on purpose. This isn't a malfunction or programming error, but rather a deliberate strategy that scientists have discovered makes artificial intelligence more intelligent and trustworthy. Strategic forgetting represents a paradoxical breakthrough where selective amnesia enhances machine capabilities. The field is undergoing revolutionary transformation at breakneck speed, with AI systems evolving from simple pattern recognition to sophisticated entities that understand their own limitations while respecting the fundamental laws of nature. These 18 papers reveal discoveries that fundamentally change how we conceptualize intelligence itself. We're witnessing models that learn to understand their own limitations, neural networks that solve complex physics equations while maintaining respect for natural laws, and systems that bridge abstract mathematical theory with world-changing practical applications. This revolutionary transformation is happening in real time, as researchers develop AI that can grow, adapt, and maintain knowledge throughout their operational lifetime, while becoming increasingly sophisticated and reliable. Machine learning represents the art and science of teaching computers to learn from experience, much like how a master chef develops intuitive understanding of flavors through years of cooking, tasting, and adjusting recipes. This field sits at the fascinating intersection of mathematics, computer science, statistics, and cognitive psychology, where abstract theoretical frameworks meet practical problem-solving. Unlike human learning, constrained by biological limitations, machine learning processes vast amounts of information at incredible speeds, discovering patterns that would take humans lifetimes to uncover. These systems power everything from Netflix recommendations and navigation apps to critical applications in medical diagnosis and autonomous vehicles. Foundation models represent massive neural networks, functioning like vast digital brains with billions of interconnected neurons. Boursier and colleagues made a remarkable discovery about attention mechanisms in these systems. When processing extremely long sequences of information, the complex mathematical operations powering attention mechanisms begin behaving like much simpler linear operations. This phenomenon resembles how complex symphonies gradually become simple melodies when played for extended durations. This finding is revolutionary because it enables researchers to apply simpler analytical tools to understand these complex systems, providing new insights into how large language models process extensive contexts and offering pathways for developing more efficient architectures. Adaptive learning addresses one of the most human-like challenges in artificial intelligence: acquiring new knowledge without forgetting previously learned information. Humans excel at this capability, learning new languages without forgetting their native tongue, or mastering new skills while retaining existing expertise. However, this has proven remarkably difficult for machines. When neural networks learn new tasks, they often experience catastrophic forgetting, analogous to a student forgetting algebra after learning calculus. Researchers are developing sophisticated architectures that maintain multiple expert systems and intelligently determine which expertise to apply to each new situation, creating AI systems capable of growing and adapting throughout their operational lifetime. Physics-informed AI represents a paradigm shift from purely data-driven approaches to methods incorporating domain knowledge and physical principles. This approach resembles predicting weather using historical temperature data, combined with understanding of atmospheric physics, fluid dynamics, and thermodynamics, consistently producing more accurate and interpretable results than data-only methods. Researchers are developing differentiable programming frameworks that make traditional physics simulations learnable, enabling AI systems to discover new physical relationships while respecting known natural laws. This knowledge-integrated methodology bridges the gap between theoretical understanding and practical application, creating more reliable and scientifically grounded artificial intelligence systems. 5 revolutionary breakthroughs emerge from this research collection, each representing significant leaps in machine learning understanding. First, softmax attention mechanisms become linear operations when processing infinite-length prompts, simplifying complex mathematical analysis. Second, geometric methods reveal system interactions through characteristic L-shaped curves, like determining pond shape by observing ripple patterns. Third, hybrid models combining physics solvers with neural networks outperform either approach alone. Fourth, spectral subspace methods substantially improve federated learning security against malicious attacks. Finally, brain imaging analysis achieves breakthrough stability using semantic tokenization approaches, focusing on functional networks rather than noisy individual signals. Our paper of the day focuses on Boursier and colleagues' work on softmax as linear attention in the large prompt regime, representing a significant theoretical breakthrough in understanding transformer architectures. This research addresses fundamental questions about mathematical foundations of attention, mechanisms powering today's most successful language models. Softmax attention has been the cornerstone of transformer architectures, but its nonlinear nature made mathematical analysis notoriously difficult. The researchers investigated what happens when these mechanisms process very long input sequences, a scenario becoming increasingly important as applications demand models capable of handling extensive documents, long conversations, and complex reasoning chains. The team's approach demonstrates mathematical elegance and rigor, leveraging measure theory to establish analytical foundations. For inputs following independent and identically distributed Gaussian distributions, they prove that softmax operators converge to linear operators acting on underlying input token measures as prompt length approaches infinity. This isn't really asymptotic theory. They establish non-asymptotic concentration bounds quantifying how rapidly finite prompt models approach their infinite prompt counterparts. The gradients also exhibit concentration properties, ensuring training stability. Their in-context linear regression analysis provides concrete examples of how this theoretical framework applies to specific learning scenarios. This mathematical discovery carries profound practical implications extending beyond immediate applications. The finding that optimization techniques developed for linear attention become applicable to softmax attention under appropriate conditions opens new research and development avenues. Years of painstaking mathematical analysis went into developing new proof techniques and analytical tools for handling attention mechanism intricacies. This work bridges abstract measure theory with practical machine learning applications, contributing to growing theoretical understanding that explains modern neural architecture success. It provides principled guidance for architectural design and optimization strategies as we continue scaling language models and extending their capabilities. Looking toward future horizons, this research collection paints an optimistic picture of machine learning's trajectory, resembling a vast garden where different approaches cross-pollinate to create hybrid varieties with unexpected capabilities. Physics-informed learning integration promises to revolutionize scientific computing, accelerating discovery across climate modeling, drug discovery, materials science, and astrophysics. Interpretable AI development addresses pressing challenges as systems become more capable and widely deployed. Continual learning advances point toward AI that grows and evolves like biological intelligence. Hybrid architectures combining different computational paradigms suggest more flexible, capable systems, leveraging symbolic reasoning, neural network pattern recognition, and probabilistic method guarantees. Today's journey through cutting-edge machine learning research reveals a field undergoing rapid transformation, where theoretical insights drive practical innovations and practical challenges inspire new theoretical frameworks. From attention mechanisms that simplify with long contexts to hybrid systems combining physics with learning, from interpretable models explaining their decisions to adaptive systems learning without forgetting, we're witnessing the emergence of more sophisticated, reliable, and capable artificial intelligence. This work represents thousands of research hours by brilliant minds worldwide, each contribution building toward a future where artificial intelligence serves as a powerful tool for human flourishing. This research summary was synthesized using GPT Anthropic CLAUDE-SONNET 4-202505514 with TTS synthesis powered by Deepgram technology and image generation capabilities through OpenAI systems. Human expert review was conducted for accuracy and coherence, though some oversights may exist. All references are provided for further exploration. The synthesis process involved careful analysis of 18 papers to extract key insights, while maintaining technical accuracy and creating coherent narrative flow suitable for podcast presentation. Thank you for joining us on AI Frontiers today. I encourage you to explore these papers yourself and share your thoughts with colleagues and peers. Subscribe to AI Frontiers for daily research insights and join our community of researchers, practitioners, and enthusiasts. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.